Huiling. I am a PhD student working with Professor Zbigniew Korbocek and Professor Ravi Iyer here at the University of Illinois. Right now, I'm going to present some of my work to building the specification-based intrusion detection system for the DNP3 protocol. In today's power grid, actually, the SCADA system will deliver the information based on the IP network, such as the sensor measurement or control command. So this introduced some critical threat model to the power system, as the control command, if it's maliciously crafted, can directly change the system's physical state. So we focus on what we call control-related attacks, in which the sophisticated attacker can exploit the system vulnerabilities and also using just a few maliciously crafted control commands to put the system into the insecure electrical states. Here I'm using this graph to just briefly show the impact of this type of attacks. The previously research will focus on the corruption of the measurement. So as a result, the state estimation that in the control center may estimate the wrong system state. Our focus, however, is on the SCADA master or the similar commercial software to issue the command that can change the power system's physical configuration. Actually, in my current work right now, we try to map in this changing of the physical configuration into the mathematical representation of the power system. Due to the time limit, however, we will not focus on this we will not describe this in details in this presentation. In addition to putting some impact on the power system's physical state, this type of control-related attack is also hard to detect. It is hard to detect based solely on the power system's electrical states. The traditional contingency analysis considers only the low-order instance. For example, the N-1 contingency considers only the outage of a single component, but the attacks can make the wider system changes. The traditional state estimation is performed periodically, so it may detect attacks, but probably after the physical damage. What makes things worse is that measurements that deliver to these two types of analysis may be corrupted during their communication. It is also very hard to detect based solely on the network intrusion detection systems, because the commands can be encoded in a correct syntax, so making it not detectable based on the traditional network IDS, which relies on the protocol level anomaly. So in order to detect these control-related attacks, we propose combining the system knowledge of both cyber and physical infrastructure in the power grid. Put in one sentence says, we integrate the network monitoring with the look-ahead power flow analysis. As a result, we can detect the malicious command at their first appearances instead of identify the physical damage after the fact. Again, I'm going to use this graph to describe how we apply our detection mechanism. For the cyber infrastructure, we adapt the specification-based IDS for the SCADA systems. This type of IDS will detect the unexpected network activities based on the predefined security specifications. And specifically, we adapt BRO, which is a runtime network traffic analyzer, to support the SCADA protocols. For example, we developed the DNP3 and Modbus analyzer in BRO's distribution, which is also you can download from the BRO's website. And we have developed a collaboration with the industry partners such as the Amron and Iberlab here in the University of Illinois. We use the real network traffic, anonymized from the substation in Amron, to test our developed tools. For the cyber infrastructure, we developed a semantic analysis framework to augment the network IDs with the power flow analysis capabilities. Specifically, the developed IDS can monitor network payloads to identify the control commands, and based on the parameters of those control commands, we invoke the look-ahead power flow analysis to evaluate the physical consequence of those commands' execution. Of course, at the same time, actually, we can also monitor the sensor measurements during their to identify any corruptions during their communication between the substation and control centers. And as we mentioned, we actually exploit the power flow analysis to perform some detection. However, the classical AC power flow analysis can calculate very accurate system state, but usually it may introduce very long latency. The DC power of analysis can introduce very little latency, but calculates a very inaccurate system state, so it may generate a lot of false positive and false negative detections. So we propose actually to adapting the AC power flow analysis to balance the detection latency and accuracy. As a result, we can allow some timely responses before the system-wide propagation of the malicious damage. Specifically, we are adapting the iterative algorithm. In our experiment, is the Newton-Raphson algorithm by reducing the number of iterations that you calculate the system states based on the control command that we observe at the runtime. This reduction can be made intelligently to meet the trade-off between the detection accuracy and the latency. Here I'm going to just present several evaluation for the adapted algorithm that I've just mentioned. It is performed on a testbed, and we're using the case file of the IEEE 24 bus, 30 bus, and 39 bus, and also a 2760 36 bus system that is included in the MatPower to perform the evaluation. This 2000 bus system represents transmission networks in Poland during the summer of 2004. And the malicious changes that are carried by those commands that we considered is including the multiple line outage, the generation, and the load modification. We put in those changes into these case files, and using the AC power flow analysis, DC power flow analysis, and the adapted algorithm to evaluate the consequence. In this figure, in this table, we compare the detection accuracy in terms of the false positive and the false negative based on the between the adapted algorithm and the DC power flow analysis. Due to the time limit, we can just focus on the 30 bus system, which is introduced the most false negative detection by the DC power flow analysis, can be as large as 20%. And with the help of the adapted algorithm, we can reduce the number to 0.01%. And a similar reduction can also be shown in this false positive detection, reducing the number from the 2.6% to 0.78%. And in this figure, we briefly showed the detection latency between the AC power flow analysis, DC, and also the adapted algorithm. The x-axis of this figure indicates a different type of power system we considered, and the y-axis indicates the detection latency in a millisecond. Because the detection latency introduced by the difference between a large-scale system and a small-scale system can be of very different magnitude, so we amplify the detection latency for the small-scale system on the separate figure on the right side of And we can see that compared with the AC power flow analysis, we can reduce detection latency significantly, especially for this large-scale system. We can see as much as 60% reduction. And in conclusion, that we combine the system knowledge of both cyber and physical infrastructure in Power Grid to detect these control-related attacks. And we developed the network IDS for the proprietary protocols using the Power Grid. We augment the network IDS with the semantic analysis to estimate the physical consequence of the command execution. In order to balance the detection latency and accuracy, we dynamically adapt the AC power flow analysis specifically for our detection purpose. And thank you for your attention. And feel free to stop by our poster. And I also prepare a simple demo around my poster. Thank you.